So here we are picking right up on that idea of forming ions from the first section of Chapter 5. Now we're ready to think about how we take these compounds, these ionic compounds, and figure out more about their behavior. Keeping in mind that there are always exceptions, and chemistry is certainly not a content area that's void of exceptions, we'll take a look at some of the common themes with ionic compounds and realize that these are mainly what you'll expect from ionic compounds that you'll encounter in this course. But of course, things are always being pushed to the limits of understanding, and we have some really neat things like ionic liquids and other more recent developments with ionic compounds at room temperature and pressure. Okay, so promptly ignoring those interesting things like ionic liquids, we'll say that ionic compounds consist of positive and negative ions. That's always true. That's what makes them ionic. They have attractive forces between the positive and negative ions called ionic bonds. And so that's what's holding them together. And so this is a full transfer of electrons, which results in a full positive charge for the cation and a full negative charge for the anion. So that's quite a strong interaction. So therefore we have high melting points and high boiling points usually. And these ionic compounds are therefore usually solids at room temperature. I've already mentioned that ionic liquids are a pretty big development in the last few decades, and they're obviously liquids at room temperature and pressure, but they're exceptional, they're unusual. The stock ionic compounds are typically solids at room temperature and pressure because you have that really strong force of the full ionic bond to overcome to make a liquid or a gas phase substance from those ionic compounds. So if our goal is to keep chemistry simple, and believe it or not, that's one of my goals, at least keep it simple enough, but yet give you what you need to know from the course, we'll think of salt. Sodium chloride or table salt is our classic ionic compound. So it helps to have something in mind when we're talking about these things. And salt, table salt, sodium chloride, is a really good example. It's a solid like we'd expect. It has very regular pattern to it. It has +1 and -1 ions, which is the simplest type to think of. So it's a pretty good candidate for our classic ionic compound. So think of sodium chloride, and for the most part, at least at the level you need to know for this course, you've got yourself a pretty good candidate for an ionic solid. The other thing that sodium chloride will do for you, although it's an unusual one in this regard, it'll give you an idea of how we do the formula. The chemical formula of ionic substances involve the chemical symbols and subscripts with the subscripts representing the lowest whole number ratio of ions. Sodium chloride is a really easy one because we don't show any subscripts, because there's one sodium ion, which is a +1, for every one chloride ion, which is a -1. So in that regard, it's maybe not the best example of an ionic compound, but it certainly gives you a valid chemical formula of NaCl. Notice that the sum of positively and negatively charged ions is always 0, because the charges always have to be balanced to get a neutral compound. So the total positive charge has to equal the total negative charge. And sodium chloride, obviously a good example, but a fairly simple example in that regard. Na +1, Cl -1 to give our NaCl formula. So if we're looking at our process again, we have the neutral sodium atom loses 1 electron from its valence to now gain the electron configuration of neon, a stable octet. The chlorine gains the 1 electron to become like argon, to have a stable noble gas configuration there. And when we write the symbol for our sodium chloride, our salt, we always write the symbol of the metal first and then the symbol of the non-metal afterward. And for the formula of the compound, we shouldn't have any pluses or minuses, no superscripts, but as we'll see, we will end up with subscripts quite often, although sodium chloride has none because of the +1 and -1. We don't show the ones as subscripts. Okay, and here we go with a slightly more difficult case, getting charge balance for magnesium chloride. So instead of sticking with group 1, where they'd always be in a 1-to-1 ratio, we move over to group 2 metals, and we see magnesium being a 2+ is going to need 2 Cl- to charge balance it, right? Because in magnesium chloride, we have that magnesium atom losing 2 valence electrons to become an Mg2+. That means we need 2 of the Cl-. Each Cl atom gains 1 electron of those 2 that the magnesium lost, and we now therefore need subscripts in order to indicate the number of ions, at least for the chlorine, which has now become the chloride ions. So we still write the symbol of the metal first. If there's a subscript of 1, we ignore it, just like we did in the case of sodium chloride. We don't say Na1, Cl1, we just say NaCl. Here we just say MgCl, and now we show the subscript of 2 for the chloride, which has 2 -1 ions. One of the tricks to it is to look at the charge on the metal or the nonmetal and swap that sort of diagonally. So take the 2 from the Mg2+ and make that the subscript of the chlorine in the chemical symbol, and take the charge of the 1- from the chloride. Again, just the number part, the 1 goes right after the magnesium, and obviously we don't show it, so that's one way to get MgCl2. It doesn't always work. You have to be careful because these are the simplest whole number ratios. So if you end up with a case where we could divide, let's say we have, tin 4 oxide. So that would be tin with a 4+, oxygen with a 2-. If we swap them, we'd end up with SN2O4, which would really reduce to SNO2 when we divide both by 2. So as long as there's not a common factor, you can leave it, but realize there will be times when that approach will not work directly. You do have to do the lowest common multiple. Okay, we see another example here now with sodium ion and nitride ion. Sodium's a +1, nitride's a 3-, so we would need 3 of those Na+ to get our neutral Na3N compound. So 3 times the 1+ plus 1 times the 3-, or like I said, swapping. If you take a look at the detailed problem solving video there, I think there's an example where I show that swapping approach, and just be careful, it doesn't always work directly. Sometimes you do have to massage it at the end, but it's a nice quick approach that gets you there most of the time. And again, as long as you're careful to check it at the end, you'll always get the right answer if you have that common factor that you have to divide out. All right, and here we see the other example. Just like with sodium nitride, now we have sodium sulfide. Again, we need multiple sodium ions to balance that charge of 2- on the sulfide. So the first time we saw it was the magnesium was 2+. Now we see it with sulfur being a 2- sulfide ion. Therefore, we need a 2 in front of the following the sodium, and we don't show the 1 following the sulfur. It's understood to be there. So when we have these ionic compounds, the smallest formula, what we give, the group of ions with the lowest whole number ratio of ions in the ionic compound, is called a formula unit. So these are not molecules like we'll talk about with the smallest unit of covalent bonding. These are ionic formula units, and just be careful about that. Sometimes people get lazy in their nomenclature and deal with molecules all the time, but these are not. They're ionic substances, so their smallest ratio of ions, smallest whole number ratio, is called a formula unit as opposed to a molecule. Alright, so again, summarizing with one final example here, we have the challenge to write the ionic formula of the compound containing barium 2+ and chloride 1- ions. We have the symbols, Ba2+, Cl-, balance those charges. If there's the 2+ from the barium, we need 2 -1s of the chlorides. And then we would write the metal first. We don't show a subscript after the metal of 1 if there's just 1. Anything else we would show. And then we write the nonmetal second. And in this case, we need 2 chloride ions to balance out the 1 barium 2+ ion. So this approach works great. If you want to take a look at that other approach I mentioned, where you're just swapping the charges for the subscripts and then checking at the end to make sure that they're not present in some multiple of 2 is usually the problem case. Go on in, check out the worked example problem folder. Then there's a problem-based video folder, and I think it's the second video there will show you how to deal with that particular case. Okay, so before we end this subtopic of Chapter 5, let's go ahead and do one last learning check and see how you do with selecting the correct formula for each of the following ionic compounds. So if you make a compound for number 1 based on sodium ion and sulfide ion, what should be its correct formula? For aluminum ion and chloride ion, what would you expect its formula to be? And finally, for magnesium ion and nitride ion, what would you expect the formula to be in that case? So go ahead, pause the video, make your selection, and we'll start back up to see how you did. Okay, so number 1, we're looking for sodium and sulfide, and therefore we would need Na2S, right? 2 of the sodium plus 1s to balance out the sulfur 2 minus. For number 2, we now need 3 of the Cl minuses to balance out the Al3 plus, and that gives us choice A, AlCl3. And finally, for the third example, magnesium 2 plus and nitrogen nitride 3 minus gives us Mg3N2, and that's where it's really convenient to do the swapping, but again, just go back at the end and make sure you don't have a common factor. Usually it's some sort of common factor of 2 that gets you in trouble. In this case, we don't have any such thing going on. The 3 magnesiums at 2 plus gives us a total of 6 plus. The 2 nitrides at -3 each gives us a total of -6. 6 plus 6 minus balances out to give us a net 0 charge. This is another area, as I've said before, practice, and try to practice some more unusual things like the magnesium nitride. It was probably the trickiest one here because we haven't done a whole lot with those 3 minus ions. Try to do the 3 minus and the 2 minus and the 3 plus and the 2 plus and mix those together to challenge yourself and make sure you're really comfortable with this. But certainly reach out to me if I can be of any assistance as you're getting used to writing ionic compound formulas.